Well, welcome back. We are at Quantitative Social Science Methods, Gov 2001, Gov 1002, and E200. We have done the overview and logistics, and we've done the data generation processes, and we've talked about probability, and now we're going to switch from probability to inference. That's really the key here, right? Because probability gives us a model. It's a model of uncertainty. It's a very successful model, but it assumes the model. It assumes the stuff we want to know, and then it shows what happens when data is drawn from that universe. It was very good to be able to describe that universe, and it's really useful for us to have a set of tools, probability tools, in order to describe worlds. But it's our task now to do the opposite. It's our task now to take what we see out there in the world, data, and try to make an inference back to what the actual world really is like. And so that's what inference is. That's what we're going to talk about today. So let's get started. Let's get started with a click in the right place. There we go. Okay, so here's the layout of what I'm going to talk about. Today, in this set of slides, I'm going to talk about the impossibility of inference without assumptions. It's just a few slides. And then I'm going to give you an overview of 3 theories of inference. I'm going to talk about likelihood, I'm going to talk about Bayesian inference, and I'm going to talk about the Neyman-Pearson hypothesis testing paradigm. So we have 3 theories of inference, 3 ways of using facts you have to learn about facts you don't have. Those 3 ways don't necessarily agree with each other. I mean, they don't agree with each other. There are parts of what they have that they have in common and parts that are completely divergent. There isn't one way of necessarily getting from the facts we have to the facts we don't have, because those facts that we don't have may have nothing to do with the facts that we do have. So there are a lot of ways of getting from one to the other. There are a lot of theories of inference. We're going to introduce these 3 because they seem to be the main ones, but be open to the possibility of others. This gives you an overview, and then we're going to zero in on likelihood, which is going to be tremendously useful for us. I'm then going to stop. I'll stop at about slide 20 if you want to watch my progress today. Okay, so the impossibility of inference without assumptions is where we're going to start. All right, so when you took the class before this one, when you took your intro statistics class, I'm sure at some point the instructor had on the board a set of dots, okay? And they said, and you may have said, or somebody had said, we're going to draw a line to fit to the dots. We have x on the horizontal axis, the explanatory variable, an explanatory variable. We have y on the vertical axis. And the question is, how do you draw a line to fit the dots? Okay. So what's the rule? What's the rule? Well, the rule could be least squares. And I'm sure that the instructor said, well, what we want to do is we want to draw this line such that we're going to minimize the sum of the squared residuals. Now, I know that you probably thought to yourself, or at least many of you thought to yourself, that wait a second, why are we taking the squared differences between the points in the line? Why don't we just take the absolute differences between the points in the line? Isn't that simpler? And if anybody in your class actually asked the question, the instructor in that class, I'm sure gave the answer that all the other instructors give, which is no. It's some kind of reasoned answer, something like, no, what we want is we want to penalize deviations that are farther from the line proportionally more than those that are near the line. And if you square the deviations, that exaggerates the influence of the ones farther away to make sure that we don't get ones farther away when we're selecting the line. And at least when I saw my instructor in school first saying that, I thought to myself, how come I don't just minimize the sum of the absolute deviations? And if you remember somebody asking that, they sort of go like this. The actual answer, the real answer, the reason that you got taught least squares rather than absolute deviations, if the goal was to fit a line to a scatterplot, do you know what it is? It's just simpler mathematically, that's all. There isn't really a substantive answer. It's just simpler mathematically. In fact, actually, minimum absolute deviations is a thing. It is possible to do. It's not that hard. It's mathematically a little more complicated, but it absolutely could be done. Okay, so how do you fit a line to a scatterplot? Well, one possibility is some rule. Let's take that up a level because after all, now that you know that you can do it both ways, which way are you supposed to choose? Which is the better way? That's not at all clear. So another way is, well, we could do it by hand. We could just take a line and see where it fits. As it happens, people have studied that. They've studied what rule do we as humans choose when we draw the line, right? Is it minimum squared deviations, minimum absolute deviations? Actually, what it tends to be is the principal component line, which is, so think about minimum squared or absolute deviations. It's vertical deviations. You're using x to predict y. So if you have a line and you're predicting the deviations, it's the vertical error, right? So principal components, it's the error of the dot closest to the line. Is that right? Is that plausible? Is that more substantively meaningful? I don't know. It's just like a rule. Like why is it better? Humans tend to do that. So if you study psychology, that's an interesting fact, I suppose, about human choices. I don't know why out there in nature, when we evolved this way, or why, or when we were roaming around the savannah, we had to choose which way to fit points to a line. But that's apparently the way that we came up with. So another possibility, another level up, is we could pick a statistical criterion, which is a bit more principled. We could say, we wish to choose an estimator that is unbiased or efficient or consistent, or unbiased and consistent. And there's a whole lot of these estimators. We could do that. You may have heard of, you may have even studied the Gauss-Markov theorem, which is one way of choosing a set of principles. And once you have that set of principles, then you can derive the method that enables us to fit the points to the line. And so if you choose unbiasedness or minimum variance unbiasedness, then the Gauss-Markov theorem shows you that the line that you should draw is least squares. That's interesting because you don't start off with least squares. You start off with a statistical principle, and then least squares is just derived as a consequence. So that seems a little better. But why those criteria? Why not some other criterion? Right? So a better way is to have a full theory of inference and make the choice for a specific substantive purpose, like a causal estimate. Like you have a reason, a good substantive reason to choose a causal estimate, to choose a particular causal estimate as a quantity of interest to go after, or a prediction, or something else, something of specific interest to you. Okay, then we could use one of the theories of inference that I'm going to describe to you, or some other, to take all the facts we have to get to this one fact that we don't have, this causal effect, this effect of something on something else, or this prediction, or whatever it is. That's the thing that we have. And then, as a consequence of that theory of inference, which you can decide whether you want to accept that as the way of getting from the facts you have to the facts you don't have. But if you do, then that will give us an estimator, and that estimator will be something like minimum squares or minimum absolute deviations, and the particular rule shouldn't really matter to you. It's not really the point. The real point is that you're going to follow this theory of inference. In addition, this theory of inference will tend to give you estimators with certain statistical properties. That is, it's just like the criteria. They may be unbiased, they may be consistent. And if you follow a particular theory of inference, you may wind up with those criteria. So this is the way that we're going to pursue it. If you put this all together and you think about the question, how to fit a line to a scatterplot that your professor in the last class put up on the board, and you think about that question, it's sort of a dumb question, isn't it? Right? We don't start out doing research by asking how to fit a line to a scatterplot. It's not a good question. It's not an interesting question. It's something that you do along the way. Okay? So we're going to start with the question, and it may be that what we need to do with this question is we're going to fit a line to a scatterplot. We're going to figure that out. Okay? So so the quantities of interest. I want every time you do a statistical analysis, I want you to know what the quantity of interest is. To be fair, you don't know what the quantity of interest is every time when you start, but at some point you're going to have a quantity of interest. Now, quantity of interest could just be a summary of the data. It could be a function of the facts you have, no problem. It's straightforward to do that. You don't need inference in order to summarize data. You can choose to summarize the data any way that you find useful, intuitive, and an easy way to take a big data set and stick it in your head or summarize it or get intuition from it. That's summarizing data. Inference is fundamentally different. It's using facts you have to learn about facts you don't have. So you can look at our overall little graph here. So the goals of empirical inference, summarizing data versus inference. So inference can be descriptive or it can be counterfactual. Descriptive inference are inferences about things that exist. So if you want to know some facts that exist, that already exist, that are out there now, but you just happen not to have them, and you may not actually know them. What's the average age in the United States population? That's not a knowable fact, like exactly, because even the census is not remotely exact. But we can make an inference about it if we have a sample of people. So, but it exists. It's out there. It's a specific thing right now. Inference also includes counterfactual inference. And counterfactual inference is trying to find out things that don't actually exist, but might exist in the future for predictive inference, if the world were different for what-if questions, and causal inferences, which is basically the difference between the actual state of the world and a what-if question. What would happen if we intervened and implemented this public policy program? So a what-if question is, what would happen if we intervened and implemented this public policy program? A causal inference is the difference between what happens now that we didn't do it and what would have happened if we go back in time, implement it, and see what happens. And it's the difference between the two numbers, let's say the fraction of people that turn out to vote, or the fraction of people that are unemployed. If you look closely in the bottom right-hand corner here, it looks like we've introduced a special terminology, causal inferences. And causal inferences are causal inferences for people who can't spell. Just so you know, we've put that in there especially for you. One more page. All right, so what's the problem of inference? Why is it that we're doing this? Inference is the opposite of probability. Here's probability. Probability is the probability of something that's known given something that's unknown from our perspective in doing data analysis. Okay, so typically in probability, you assume a model. You assume it's a fair coin with probability heads 0.5. That's the model. That's the thing we might like to know. That's why I'm going to call it unknown. Given that, probability tells us the odds, the probability, the likelihood, the probability of getting different results. So once we know the model and we know probability, we know what all the data that comes from that model will look like. That's probability. Probability of known given the unknown. Inference is exactly the opposite. In fact, for a long time in the literature, there was the goal of trying to figure out inverse probability, which we can think of as inference, but it's not exactly. Okay, so inverse probability is the exact opposite of probability. It's the probability of the unknown thing given the known thing. Now, that's what we want, right? That's what it feels like we would really like to go after. The probability of something we don't know, right? Is it this, or this? I want to know the probability of each one of those things given all the facts we know. That's what we would really like. Well, that's called inverse probability. And if you want to get those as absolute numbers, absolute probabilities, turns out it's not possible. Just mathematically impossible. And if you think about it, there's no way that it could ever be possible, right? So you condition on the data you have, which is such a tiny fraction of the entire universe of knowledge. And then the unknown part is like anything that could happen in the universe, right? And we're supposed to come up with an absolute metric of probability for that. It ain't going to happen, okay? And that's basically what the literature concluded. Inverse probability as an absolute measure of the uncertainty of any possible outcome, it's just not going to happen. But yet we sort of want that. Okay, so let's fix the problem in 2 steps. The first problem is we're going to go after a more reasonable but limited goal. Not the first problem, but the first approach to a solution. So a more reasonable but limited goal is, let's take the unknown part, the M, the model, And let's break it into two pieces. First is theta, the thing that we're going to go after, some very specific quantity of interest, right? The percent of people with a particular characteristic. And m star is going to be everything else, okay? So m is m star m theta. Theta is going to be the specific thing, maybe a set of parameters, and m star is all kinds of other stuff, okay? If we divide it up that way, what we're going to do here is we're going to, right here, we're going to, this left-hand side is our solution. So what we did is we took m, we divided up into m star and theta, and we moved m star over to the right-hand side. Okay, so that's useful because basically we're just going to condition on things like the sun's going to come up tomorrow, the earth goes around the sun, like all these things that could change, but I'm not going to make any assumptions about. And we're going to focus just on the one thing that we don't know, which is our theta. Okay. And since I'm always going to assume, we're always going to assume that we know m star, I'm just going to drop it. So that's what the right-hand side of this expression is. Okay, so that's the problem of inference, and that's the first step that we're going to take towards reasonableness. We're still going to be assuming a whole bunch of stuff, and it's not going to be possible to get rid of all of the assumptions in inference, and that's the point of this equation. All right. 3 theories of inference. So I'm going to give you likelihood, Bayes, and Neyman-Pearson hypothesis testing. So here's just the overview of all 3. We will learn how to use these in great depth so that you can use it in your research later on. Okay, but first I want to give you the overview so you have a general sense of what's going on, and then we will get into the details. Right now, just the overview. All right, so we're going to build some theories of inference. Everything on this particular page is true. As a political scientist, I love to be able to use that sentence when I can. It's not common. There's no assumptions I'm going to make on this page. Okay, first thing is I'm going to give you Bayes' theorem. That's different than Bayesian inference. Okay, Bayes' theorem is just true. It's just a theorem. Okay, so we're going to have the probability of theta given y, the unknown given the known, and remember m star is everything else, which we're going to assume. Okay. So that's conditional probability, and the rules of conditional probability is you get the conditional probability by taking the joint probability, which is both theta and y, and dividing by the marginal probability. So it's the probability of A and B divided by the probability of B, and then you get the probability of A given B. So this is just by definition very, very simple. I'm going to extend that by taking the numerator, which is a joint distribution, and I'm going to divide it up into 2 things, into the factor of 2 things, the product of 2 things. And so we have the joint probability. You can see on the right-hand side it may be a little more familiar. In fact, if you take the probability of A given B on the right over here on the right-hand side, and you leave that there, and you take the probability of B and you move it to the denominator here, you have the definition of conditional probability. So I just took the probability of B, which is in the denominator, and I put it up over here. And so now I'm going to take this joint probability, which is an example of this joint probability, and I'm going to replace it by a conditional and a marginal, by a conditional and a marginal. So same exact story. Okay. So that's all. I mean, everything's true. I just replaced it. Okay. Next thing is, it looks a little complicated, but it's not. So I have the denominator here, P of y. So what's P of y? Well, P of y is equal to P of theta given y integrated over theta, collapsed over the theta dimension. So that's the idea, right? So you take the denominator, which is P of theta given y, summarize it as P of theta times P of y given theta, right? Because this is the same as this. Stick that in here, and then just collapse it over the theta dimension, right? Done over the theta dimension, right? That's what I told you. Like what we have is theta going this way and y going this way, right? And there's, you think about it as like there's a bowling ball on a bed with a sheet on a bed. You put the bowling ball on the sheet, you freeze the whole thing in liquid nitrogen, you turn it upside down, and it looks sort of like a normal distribution, but in 2 dimensions, right? Okay. So now one dimension is theta, and the other dimension is y. Okay. But we want to get rid of the theta dimension. So how do you do that? So if y is going this way and theta is going this way, what do? Well, you scoop it this way. You get a bunch of scoops, right? Like, tractors. If you ever saw Soylent Green, they come in with the scoops, right? So they scoop this way. And if it looked like like the bowling ball on the sheet, frozen in liquid nitrogen and turned upside down, okay? And you scoop this way, or you get a bunch of cars and you put them over there and you shine them this way and up against the wall. What does it look like? Well, it looks sort of like this, right? It's the marginal distribution, okay? And it's the distribution of y because we've collapsed over the distribution of theta. So that means the denominator here is just the numerator collapsed. No big deal. Okay, now, why am I telling you all this? I'll explain why I'm telling you all this. Okay, if we knew the right-hand side of this expression, then we could compute the whole inverse probability and we'd be great, right? That's really what we would have liked to get. So all we need to know is the different pieces of the right-hand side, all right? Now, theories of inference arose to interpret, it turns out, this result. Like the likelihood theory of inference and the Bayesian theory of inference both arose to try to explain this equation. So if we can understand this equation, we can derive likelihood as a theory of inference and Bayesian inference as a theory of inference. Okay, the equation here is true, but those are the different theories of inference. Okay, so now we know what the denominator is because it's just a function of the numerator. So there's only two things here that we have to figure out. It's p of theta and p of y given theta. That's the whole thing. Okay. In both of them, p of y given theta, that's a traditional probability density, right? Because that's the probability of the known given the unknown. It's the probability of the data, right? You know, whether they're zeros or ones, given that it is a fair coin. Right, so that's a traditional probability. All probability distributions are written down that way as p of y given theta. Okay, so we're almost there. We're almost to the inverse probability. Just so you know, you're not going to get there. Although if you do figure it out, definitely give me a call, like right away. Okay, you're not going to get there. Okay, so the two theories of inference, likelihood and Bayes, differ completely on the rest of the stuff, on how you interpret everything but that one thing in the numerator. Okay, so let's talk about likelihood and then we'll talk about Bayes so we can understand them. So this is the first interpretation of that equation. It's the likelihood theory of inference. Okay, so this was R.A. Fisher's idea, or Sir R.A. Fisher to you, because he was knighted. He was also an ardent opponent of the idea that smoking caused cancer, because he just believed nobody really demonstrated this idea. And he was also paid quite a lot of money by the tobacco companies to defend that idea. So anyway, people do great things, don't always do great things, or aren't always right. In any event, theta in this theory is a fixed thing, which is, I think, comfortable to us, right? Because theta is the unknown. So it is a fixed quantity of interest that we would like to know, okay? You can think of descriptive inference. It's the average age in the United States population. We would like to know that. We don't know it. We want to know it. It is a number, okay? And why the data is random, because we can imagine it being drawn from the probability model multiple times, even though it's only drawn once. We only see it once. But that's the setup. From that setup, we add an assumption. So let me explain what this thing is. So I'm going to define this thing as k of y. K of y is just this divided by this. Now let's go over here and look at that. This is just the blue part on the right-hand side here. This is the derivation that we showed on the previous page. And if you're not sure of that, go back to the previous page. You get to do rewind in this lecture. No big deal. I'll wait. I can wait as long as you want. I'm not even real. Okay, never mind. In any event, p of theta given y is equal to this. And what the likelihood theory of inference says is take the blue and just call that k of y. We have to figure out what it means, okay? So, but nevertheless, we're going to call it k of y. And we're going to summarize the whole thing. That is, this whole thing that we'd sort of like to be inverse probability as k of y times the traditional probability. That's what we're going to aim it as. We're going to define k of y. We're going to define it as an unknown function of y. So it's unknown. We don't know what it is. It's an unknown function of y with theta fixed at its true value, which we also don't know, right? So whatever it is fixed at its true value. Okay. The likelihood theory of inference, I can now tell you the whole thing. It has 4 axioms. Remember, axioms are not true or false. They're just things that we take for granted. Okay. It has 4 axioms. They're useful if they're useful, and they're not otherwise. likelihood theory of inference has 4 axioms. The 3 probability axioms, which I've shown you before, right? The first one is the probability is a probability is a function which is greater than 0, right? Those 3. Well, probability of any event is greater than 0. The probability of the sample space is 1, and the probability of mutually exclusive events can be written down in that particular way as the sum of the probabilities of the individual events. Okay, those are the 3 likelihood axioms. But to get the likelihood theory of inference, we assume we choose those axioms and we add one more axiom, and that is the likelihood axiom. So not the likely axiom, but the likelihood axiom. Let me explain to you what the likelihood axiom is. Okay, so this is the likelihood axiom. It is the likelihood of theta given y is defined as, that's what the 3 equal signs, the 3 parts of the equal sign rather than 2, it's just is defined as k of y, that is this unknown function of the data with theta set at the true value, times the traditional probability. Okay. Now, since k of y is a constant, theta is fixed at its true value, and it's an unknown function of y, so we can just say it's proportional to, that's what that thing means. So the likelihood is proportional to p of y given theta. Now, what is the likelihood? Well, the likelihood is the right-hand side. And you say, yeah, but what is the likelihood? Okay. Well, it tells you how likely something is. Now, be careful here. That's using English to define math. Okay. And math has to be defined on its own. And so what happened here is R.A. Fisher adopted the word likelihood because it sounded sort of like probability. And he just adopted it, okay? And so now we can say, here's the likelihood of something. But just to be clear, saying that something is the likelihood of something only means this equation. It doesn't mean anything else, okay? He could have adopted a different word, okay? But that's what it is. It's the likelihood. Well, let's find out. We'll find out how useful that is, but that's the likelihood axiom, okay? You don't have to agree with it. It's not something you can agree with or disagree with. It's just the fact. Okay, the likelihood of theta given y is a function. For y fixed at the observed values, because we know what y is, remember, we at some point get to know what y is, so it's fixed at the observed values. It gives the likelihood of any value of theta you might want to try out. So once you set up the likelihood for a particular analysis, right? A particular analysis is you choose the quantity of interest, so therefore theta is defined. You don't know what the value is, but theta is defined. You choose the quantity of interest. You have a data set, so that data set it's one data set. It's a real data set with real numbers in it. You stick it in the likelihood function. You have to figure out how to calculate the likelihood function in your particular example. How do you calculate it? Wait a second. Well, okay, we'll figure that out. But you can calculate it, right? And we'll do it. We'll actually do it ourselves. But for now, you can calculate it. It's a function, right? Then what you do is everything's fixed except for theta. And you get to stick different values of theta, not real values, but just guesses as to what theta is. Any kind of guess you want. I have a whole range of values. And it will tell you the likelihood of theta equaling 12, or theta equaling 12.5, or theta equaling minus 64. And it'll give you different likelihoods. And probably you're going to choose the one that has the highest likelihood. That's roughly the idea. Likelihood, however, is a relative measure of the uncertainty of whether it's theta 1 or theta 2, whether it's 12 or minus 74. And it changes with the data. So, of course, it's a function of the data. It's conditional upon the data, right? That's important because if you compare the value of the likelihood for different theta values, you can do it within a data set because you're conditioning on the same data set. It's not reasonable to compare the value of the likelihood for different data sets because you're conditioning on different things. It's sort of meaningless. Similarly, you can't compare r squared across equations with different dependent variables because they mean different things. Okay. All right. Then there's the likelihood principle. The likelihood principle is that the data y, if y is a vector, right, and x is fixed. That's why I'm calling the data y, right? X is, we would typically think of x as part of the data also, but since it's fixed, the real thing that we get to know when we run the experiment is y. The data y only affects inferences through the likelihood function, right? Because that's it. There's only 4 axioms. Y doesn't affect our conclusions about theta in any way except through the likelihood function, so that's basically that's the point of the likelihood principle. All right, so let's visualize what this all means. To make it simpler, both algebraically and numerically, and for programming, we're going to use the log likelihood. So that's just one little step that happens here. It doesn't really change anything meaningful, except it makes your life easier. So you have to do something annoying, which is remember what logs are. And I think you probably remember not learning logs in 8th grade, right? Because that's the last time we did logs. Well, we're going to use logs. The natural logarithm, every time I say log, it's a natural logarithm. There's other logs. So you just figure out how to do natural logs. It's not a big deal. If you take the log of the likelihood, the shape of the likelihood function, which I'll show you an example of, changes, but the maximum stays in the same place, so basically everything's going to be okay. It's going to make things a lot easier for you. All right, so here's a graph. Just pay attention on the graph to the purple line. That's an example of a likelihood function. The horizontal axis is theta. Theta is the quantity of interest. The vertical axis is the log of the likelihood function of theta given y. All right, so that's what we have here. So theta's the quantity of interest. The vertical axis is the likelihood of theta, and of course given y. And you look at that thing and you say, well, some values of theta, like near here, the part that I'm going to call the maximum of the curve, which has a name. It's the maximum likelihood estimate. The maximum of this curve we could use as our estimate. We could use this as our estimate, but it would just be less likely, so it doesn't seem like a good idea. So it turns out one estimator of theta is the likelihood curve, the entire curve. You can present the whole curve. The likelihood principle, the interesting thing about the likelihood principle is we can now discard the data, right? If the model is correct, and you're willing to go with that, which you're not usually because you don't really know for sure, but if the model is correct, then you can go with the whole likelihood surface, just present it. You can publish it in your paper if you have one quantity of interest. If you have more than one, it'll instead of being a line, just this one-dimensional curve, it may be a surface or a hypersurface or things like that. But as a summary estimator, it's really important. That's all you need. You get this one-point summary if you want, instead of the whole summary estimator. If you just want one number to summarize what the effect is, you can use the MLE, the maximum likelihood estimate. And if you want to know how uncertain the maximum likelihood estimate is, you could look at how curved the curve is right at the maximum point. Now, why is that important? So on this curve, I put a quadratic approximation to this, which is an easy way of getting measuring how curved the purple surface is right near the MLE. Why does that matter? That matters because if you're interested and you believe, or you're willing to go with the idea that the maximum likelihood, that likelihood is the thing we care about, and you're going to summarize the entire curve with just this one point, then what you want to know is, are values of theta far from the maximum likelihood estimate? Are they less likely? Well, yeah, they're less likely. Are they a lot less likely or a little less likely? That's an important point. So therefore, the uncertainty of the maximum likelihood estimate is a function of how curved it is at the maximum. How fast the fall off is from the maximum, that's our measure of uncertainty. You've heard of a standard error. Standard error comes straight from that idea, okay? But we'll get to that, okay? All right, so that's likelihood. That's like, in some sense, in some general sense, everything you need to know about likelihood, although there's going to be plenty more, okay? And that's the theory of inference that we're going to go into in much more depth. Let me now talk about the Bayesian theory of inference, which builds on likelihood and takes it a little farther. And we can and will use this at certain times, okay? This idea was the Reverend Thomas Bayes' idea. He didn't like the idea at all and decided not to publish it and went off and died. In that order, but I don't think there was a causal effect. Anyway, the Reverend Thomas Bayes didn't publish this idea. It was rediscovered after his death and became quite a sensation. Okay, so let's recall the definition of conditional probability, this next step and this next step. Each of these steps are true, so that's Bayes' theorem. Okay, but Bayes' theorem is completely true, but the good Reverend interpreted this in a different way. Okay, so how does he do that? Okay, so first of all, let's take the left-hand side here. The left-hand side is P of theta given y. So he's going to call that by his own name. That's going to be called the posterior density. Posterior because it's after the analysis. Okay. Then, let's go back over here. Sorry. Then we have P of y given theta. That's the traditional probability. The traditional or proportional to the likelihood. Right, we all know what that is. That's the thing we've been doing in probability all along. And P of y, which is the denominator of this contraption, that's a constant, which is easily computed because you just take the numerator. So whatever the numerator means, we're going to have to figure that out. We're going to have to interpret it. We're going to have to define each of those things in our particular application, and we don't know how to do any of them yet. But once we do, we'll be able to get the denominator by just taking the integral, which may also be a pain, but we know that there's nothing new there. It's just a constant. So we just take the numerator, we do something to it, we get the denominator, so we don't have to think about the denominator. Okay, so think about this. The only way that Bayesian analysis differs from, the only way that Bayesian inference differs from likelihood is the prior density, right? So the denominator here is just it's a function of the numerator. The traditional probability, we already know what that is, and given a particular problem, we could choose a probability distribution that makes sense for it. If we're flipping coins, then the Bernoulli distribution makes sense. The only thing here is P of theta. And the question is, what's P of theta? According to Bayesian inference, it is called the prior density. And you've heard of the idea, that's not my prior. I have strong priors on that. This is exactly where it comes from. Okay, so what is the prior density? What is P of theta? Well, it's a probability density that represents, according to Bayesian inference, all prior evidence about theta. That is, anything you could possibly want to know about theta before you collect your data. So it's the entire summary of the scientific literature. It's all of your impressions. It's anything that you would have known, could have known, and ideally should know before you start your analysis. So it represents all the prior information. It is also, from our perspective, an opportunity, because it is a way of getting other information into the analysis that wouldn't have been there otherwise. Because the only things that are usually in our analysis are some assumptions and the data. But if you actually know a lot of other facts, it feels like you should include those, right? Like, why not? I mean, your analysis should be based upon as much evidence as possible. So it's an opportunity to get more evidence in your results. And in political science, in the social sciences, in most areas, all results are, as I said earlier, qualitative, and some are also quantitative. What that means is there's so much information out there that's qualitative. We should use that information and somehow put it in our results. And this is a way of getting it in there. A prior density is also an annoyance if you're doing Bayesian analysis, because this other information, right, that gets in there, it's required. You must summarize all prior information about theta in a formal way as a probability density distribution. Okay, so if you want to estimate some number, you have to know somehow your prior. You have to have a prior. So it's an opportunity and it's an annoyance if you choose this method of inference. It's also a philosophical assumption that non-sample information, that is qualitative information that's not in your data set, is relevant. That it should matter, as in a sense it always does, right? Even if you were running a regression last year and the only thing you learned last year was regression, obviously your data matters in order to get the results, but the specification matters, right? How you measure the variables matter, what you did with missing data matters. There's tons of other things that matter. And all of those are essentially part of your prior. And the idea here is, yeah, well, let's just also include the knowledge we have about the thing you're trying to estimate. The philosophical assumption also says that non-sample information should be formalized and included in your inferences, and that's more debatable. Maybe you want it as part of your inferences, because we should base our scientific conclusions on all prior information. It only makes sense. And maybe it should be excluded because we want this analysis to be based on this analysis, not the previous analysis. And we will combine the two ourselves. Well, maybe, but that won't be the optimal way of combining it. Bayesian analysis gives us the optimal way. So it's worth thinking about this question, and worth pausing the videotape right at this moment in order to ask yourself for an example of non-sample information you would like to be included, right? What would that be? Right? I would like to, like if I am running an analysis where party ID in political science, partisan identification, do you consider yourself a Democrat, or Republican, an independent, or what, is an explanatory variable. It almost doesn't matter what the outcome variable is. There's a big coefficient on that variable. That's a very important variable. If you're in public health or medicine, prior health status in public health measured as how healthy are you, excellent, good, fair, poor. That simple variable, that's like party ID in public health. That is a very important variable. You know, the idea that we don't know anything about that variable before you come and doing an analysis, that's ridiculous. So I would think those kinds of variables might be useful for you to go and assume some knowledge of in your analysis. Okay, so what's an example of non-sample information that you're skeptical of including, that you don't want to include? And you should think about that too. And it's worth pausing now, committing yourself to something, just thinking about it. Go ahead. Put down the beer, click on the thing. Okay, right. So anyway, so an example of non-sample information that you're skeptical of including, well, in Bayesian analysis is often brought out in situations like like a judicial proceeding, like a court case. Who did it, right? And in that case, if the judge is making a decision, it makes sense that the judge should use all of the information presented in the case and probably all prior information, right? Because you really want to get it right, and prior information really should help. Well, but suppose prior information is biased against certain racial groups or gender groups or things like that. Maybe you explicitly want to rule that information out. So what prior information you include and what prior information you exclude, it really matters. Okay. Principles of Bayesian analysis. What it enables you to do is pretty interesting. So first principle is all unknown quantities, including theta, the quantity of interest, and the random variable y, not your data set, but the random variable y across data sets, across hypothetical repeats of your data set, are treated as random variables and have a joint probability distribution of some sort. All known quantities, like the data you actually observe, are treated as fixed. We don't treat a number that you have as a random variable, we treat it as a number. That's quite intuitive. Third, if we have an observed variable b and an unobserved variable a, then the idea of Bayesian analysis is that we should be interested in the conditional distribution of a given b, of the thing that we don't know given the thing we know, which is p of a given b. That's basically what it is. And the way you get there is the rules of conditional probability. It's the joint probability divided by the marginal probability. And finally, if variables a and b are both unknown, then the distribution of a alone, which we might be interested in just one of them, we get by taking the joint distribution and collapsing or scooping over the unknown distribution. Those four principles take us very far in Bayesian analysis. Okay, so here's an example. An example of the posterior distribution of theta given y. So that's the posterior distribution. It's not the likelihood distribution, it's the posterior distribution. It's not far from the likelihood distribution, but it's the posterior distribution. And this is the way to think about it. On the horizontal axis is theta, which is the quantity of interest. On the vertical axis is p of theta given y, or the posterior distribution. We might be interested in the maximum a posteriori estimate, which is just like the maximum likelihood estimate, but it's not necessarily the same as the maximum likelihood estimate because of p of theta. but in any event, it would be right over here. So it'd be this value of theta. We can also look at how fast it drops off in each direction. Okay. So like L, the entire curve is a summary estimator. It tells you everything that you could know given this theory of inference and given your data and given your question about the quantity of interest you've chosen to go after. Unlike L, it's actually a real probability density, which is interesting because we can derive probabilistic statements. We can say the probability, given everything we've assumed, of theta being between two values is just the integral under the posterior distribution between two values. That enables us to say things that are sort of coherent, like the probability that he did it is 0.2. The probability of the average age in the population being between 57 and 64 is exactly this number. You can't do that in likelihood, in the likelihood theory of inference. To compare across applications or data sets, remember I raised that in likelihood, you may need different priors because it's a whole different situation. So the posterior is relative, just like the likelihood, right, for slightly different reasons, but it's relative to the data set. So Bayesian inference, interestingly enough, obeys the likelihood principle. The data set only affects inferences through the likelihood function. What Bayesian inference does is it adds this one more thing. It adds the prior distribution. If that prior distribution is approximately 1, that is, well, now let's just be clear. A distribution can't always equal 1, because if it's equal to 1, then it's going to be 1 for all, no matter what the horizontal axis is. And then it's going to integrate to something bigger than 1, right? Because the only way that it would integrate to 1 is if we only considered the horizontal axis between two values that were 1 unit apart, like 0 and 1. But if it's constant in the relevant region of your inference, in a region in which it's substantively plausible that it makes sense, then the likelihood and the posterior distribution are the same thing. Okay, and when the prior is uniform, what that means is we really don't know whether this is true or this is true or this is true. So if we put aside the prior, then we basically get to the likelihood. So the two, likelihood inference and Bayesian inference, are very close to each other. They primarily differ in whether or not you should include prior information. But it's worth thinking about it a little more generally. So here's a summary. Likelihood simpler, start there. I suggest you start there. We are going to start there, and most of what we do is going to be likelihood. Bayes opens up more possibilities for different types of analysis. I would use it not always. I mean, this isn't a class in normative philosophy, and even if it were, there's no normative philosophy that everybody agrees with. So Bayes opens up more possibilities. If it's useful to you, then you use it. The philosophical differences between Bayes and likelihood are absolutely immense, and endless philosophical treatises have been written about the differences here. The practical differences are relatively minor, unless the prior matters. If the prior matters, then actually it could matter a lot. So here's an example where the prior mattered in work that I did. So for the World Health Organization, I did a study with Federico Girossi. We were interested, and WHO was interested in forecasting mortality rates, annual mortality rates by age and sex and country and cause. So we had 150 time series. Each time series was around 30 observations long, sometimes 20, very often only 2 observations long, because in quite a lot of the world, collecting mortality data comes from exactly where? Like it's supposed to come from the governments, but they don't necessarily collect it. So we had the best data there was, but still they weren't very long. But even if it was 30 observations long, the thing that was important to the World Health Organization was forecasting 30 years into the future. Because if you could forecast 30 years into the future, they can reset funding priorities and public health priorities. So that's what we did. We made these forecasts. We took these time series with a bunch of covariates, and we tried to predict what what mortality rates were going to be 30 years into the future. Forecasting 30 years into the future, even if you have 30 observations, is basically impossible. Doing it with 2 observations is a little ridiculous. However, what we realized is there's these patterns in demographic data. So over the age groups, what happens is if the vertical axis is log mortality and the horizontal axis, the vertical axis is log mortality and the horizontal axis is age. What happens is you're born and there's this, it's pretty risky to be born. Better than not to be born, but pretty risky. So you're at a high level of risk. And then your risk goes down over the first 5 years, and then it starts to go up. And it pretty much goes up log linearly until bad things happen. So it looks sort of like the Nike swoosh in a very stable pattern that has been stable for 350 years across data from many, many countries. So that means that some of our time series, remember we had 150,000 time series by country and age and sex and cause. And so some of the time series, we were making forecasts next to each other, like for 20-year-olds, we want to know the mortality rate 30 years ahead. And for 25-year-olds, we want to know the mortality rate 20 years ahead. And so those things were closely related. So our prior was those things are closely related. In fact, we also said neighboring countries should, in many cases, should have similar mortality rates and perhaps similar trends in mortality rates because they're spending similar amounts of money on public health. And there were all kinds of other priors, like men tend to live longer than women, and all kinds of other things that 350 years of demographic research has really learned quite a lot about. So what we did is we put those priors into our forecasting model, which is basically a regression for each one of these 150,000 units. The priors tied them all together and enabled us to borrow strength from one in forecasting the other. That actually made each one of the forecasts it made each one of the forecasts based on much more information. So it was a much more certain endeavor, and it wasn't like making a 30-year forecast on the basis of 2 observations. It was making a 30-year forecast which no matter what is going to be uncertain. We didn't predict the pandemic after all. But it was way better than if we had only used each data set entirely by itself. So priors can matter a tremendous amount depending upon what your application is. And so if it matters, it matters. That's when you should use it. Okay. Another interesting fact is Bayesians are actually happier people. Now, I don't mean that as, well, I don't mean that I mean it as a joke, but it's also serious in the following sense. If your prior is diffuse, by which I mean sort of relatively flat, so that you don't really know that much, then differences from likelihood are relatively minor, but it helps still to have the prior. Because if your likelihood function it doesn't have a clear maximum, it's hard to find the maximum numerically. And so adding a little bit of a prior makes the results much more numerically stable. Your computer programs will literally run faster and better. And if the prior isn't very strong, you're going to get pretty much the same results. And since your computer, you'll have less trouble with your computer, you'll be happier. So I'd try it. The advantages of Bayesian analysis are more information being included in your model. I mean, if you could include more data, like if you could survey 25 times the amount of observations you could, of course you should do that. Same thing. So there's more information, there's more efficiency, there's less uncertainty. There's also the development of Markov chain Monte Carlo methods, which I don't expect you know anything about at the moment, but they're ways of drawing random numbers and characterizing arbitrary posterior distributions, which turn out to be very valuable and, as I mentioned earlier, enable us to do things that we never thought would have been possible. So that's also another big advantage of Bayes. So now, it turns out there's relatively few fights between Bayesian adherents and likelihoodists. They used to be really big ones. Nowadays, we get on with our work. We choose what we want to choose. Okay, third and last theory of inference. Not last in the universe, last in this lecture. Neyman-Pearson hypothesis testing. I think you've heard of hypothesis testing, p-values, asterisks, significance, null hypotheses, all that. I'm sure you've seen this before in some guys. I'm going to give it to you one time in a relatively simple way, but I'm going to give you all the details so you get a feel for it. Okay. The fights mostly now, the philosophical fights, are between these folks, the Neyman-Pearson hypothesis testing people, and the other group, the Bayesian folks and the likelihood folks. All right, so here's the idea. The idea is there's a strict but utterly arbitrary distinction between two hypotheses, one which we'll call the null hypothesis for convenience, and the other we'll call the alternative hypothesis, H0 and H1. All tests are under the null hypothesis. That is, all tests assume the null hypothesis. We make believe the null hypothesis is true, and we do the test. We'll explain why that's the case. So for example, suppose we specify a regression where y is a linear function of x. So expected value of y is beta 0 plus beta times x. And we want to know what beta is. In likelihood, we would calculate the likelihood function. In Bayesian analysis, we would calculate the posterior distribution, in both cases of beta, because that's the thing we care about. Under Neyman-Pearson hypothesis testing, we would only do a test. That's the only thing we would do. And so an example of a test is, we wish to study whether beta is 0. And that's a not crazy thing, right? If it's 0, then x has no effect at all. If it's not 0, then maybe it has some effect. Okay. Frankly, I'd rather know what the number is, but in any event, that's the idea. Okay, so H0, the null hypothesis, is that beta is equal to 0, and we're going to test that versus the alternative hypothesis of beta being greater than 0. Yes, it could be the alternative hypothesis is that beta is greater than 0 or less than 0, but usually you have some prior information, is what a Bayesian person would say. And so let's focus on this because it's straightforward. Okay. Next step is you always choose the type 1 error rate, which is going to be called alpha, and it is the probability of deciding that the alternative hypothesis, H1, is correct when in fact the null hypothesis is really true. Okay, so often, typically, alpha, the type 1 error, is set at 0.05. So 5 times out of 100 or 1 time out of 20, we conclude that we are okay with concluding that the null hypothesis is true when in fact the alternative hypothesis is true when in fact the null hypothesis is really true. Okay, so that's the type 1 error. There's also a type 2 error where the power to detect that the alternative hypothesis is true and different from the null is a consequence of what estimator you choose, not a decision like that you do ex ante. Okay, so if you choose to take all the observations in your data set, add up and divide by n, that has more power than randomly taking half the observations, throwing away the rest, adding up and dividing by n over 2. Right? That has less power. It's not as good an estimator. The type 2 error is larger. So that's an obvious case, but there are many cases where it's not so obvious. We always want to have more power to detect the alternative. And everybody always says there's a type 3 error in which you confuse type 1 and type 2 errors. And frankly, many people confuse these and don't forget what they are, and don't remember what they are, and they have to go look them up. No big deal. All right. We then, in this particular application of Neyman-Pearson hypothesis testing, there's others, we're going to calculate a test statistic in a particular way. If we do it this way, then we're going to assume that n is large enough for the central limit theorem to work so that we get normality. So here's the idea. B, our estimator, x prime x inverse x prime y, the regression coefficient, given the assumption that beta is equal to 0, is distributed as normal, right, because of the central limit theorem, that thing is normal, with mean 0, and under the null, the mean is 0, because I just told you that beta was 0, we assume it was 0, and the variance is sigma squared b, which we can estimate from the data. Okay, so we can do that. Or we can rephrase it as a test statistic for beta, given that beta is equal to 0, which is the usual way of doing this is b, our estimator, minus the value of the assumed mean under the null hypothesis, which happens to be 0, it's beta, divided by the standard error, which is equal to b divided by the standard error. And that's distributed standard normal, right? So that's why you use standard normal, because now you can look that up in the back of the book if there's a back of the book. But you don't need that one. You can always do the previous one, and we can, now we have the null. This is the distribution of your estimator, given the assumption that the null hypothesis is true, that beta is actually equal to 0. We didn't assume anything else except for the central limit theorem that makes this normal, and this thing, and this variance we can estimate. Okay, so now we have the distribution under the central limit theorem and under the null hypothesis. So the idea here is we derive a critical value. The critical value, if we're beyond the critical value, it's going to be significant. If not, it's not going to be significant. But we derive the critical value. We figure out what it is by finding the area under the curve such that it's equal to 0.05. And so we have to figure out what's the value that makes the area 0.05, right? So we move it over until 0.05 of the area is to the right of the critical value, and then we discover what the critical value is. So the interesting thing is, it used to be the case that in educational psychology and in psychology, actually, and some other fields, they were basically strict adherents to the Neyman-Pearson hypothesis testing framework. And this was the idea. Imagine you were going to write your dissertation this way or your senior thesis. So you write your prospectus. You plan your experiment. These are fields that typically in which there's actually an experiment. You report the critical value, which you calculated, because all the number, everything I've told you so far didn't involve the data, right? So you figure out the critical value, and you write your concluding chapter before you collect your data. Think about that, right? And you explain in your prospectus that this is the decision you're going to make. Beta. I'm going to conclude that beta is greater than 0, and I was right if the test statistic, the thing that your estimator basically, is greater than the critical value. And I'm going to conclude that I was wrong and beta is actually equal to 0 if the test statistic is less than or equal to the critical value. Right. And you then first go collect your data, and you may not revise your hypothesis or your chapter. It's considered unethical. Wow, that's pretty interesting. This was once sort of discredited, and who wants to set themselves up for that kind of thing? But it's sort of making a comeback through what's called the pre-registration movement, where the idea is sometimes it's a good idea to pre-register the analyses you're going to do, which basically says what you do is you write a couple of paragraphs and you say, I'm going to do the following analyses, and if I conclude this, if I get this result, I'm going to conclude this, etc. And the idea is to tie your hands so that you are prevented from cooking the books, from playing with the data until you get the right answer. That's the idea of pre-registration. So people are doing this a bit more. In fields in which there's a decision to be made, Neyman-Pearson hypothesis testing can be quite useful. For me, I would really like to know what beta is, and it's always uncertain. So I'd like to know a point estimate. I'd like to know the uncertainty. If it passes some arbitrary threshold, I don't really care that much. But that's basically the idea. Let's have a feel for it. This is the distribution of the test statistic under the null. So it's basically the distribution of your estimator, but standardized. So under the null, the mean, of course, is 0, right? So that's a 0. This is an example of a test statistic. This is an example of your critical value that was calculated before you collected the data. The area to the right of this in red is 0.05, or whatever you decided the type 1 error rate should be. In this example, the test statistic is to the left of the critical value, and so therefore you must conclude that beta is 0, and that's it, you're cooked. And this decision, of course, will be wrong 5% of the time, because 5% of the time you would see, even if this is the correct distribution of your data, of your estimator across experiments. Remember, it's across experiments. You get one draw of the world, from the world, with one set of data. You calculate your one number, and your one number, given the setup, is one draw from this distribution. And 5 times out of 100, it's going to be out here, and so you're going to be wrong, even if this is even if the true mean in this null hypothesis, the effect of x on y, really is 0. So what is the probability it's right this time? Okay, so that's the quiz, right? So think about this yourself. So you draw a set of data, and I want you to think about the answer to the question. Not what's the probability across experiments, right? I want to know what's the probability in this experiment that you're right or wrong. What do you think about it? Okay, you can feel free to hit pause as long as you start me again. Okay, don't leave me here. Anyway, okay. So what's the probability that it's right this time? All right. So the answer is that it's right either 0 or 1, right? Because this time you've already gotten a number, right? You have a test statistic. It's either you get an estimate of beta, right? Your estimate of beta was either drawn from this distribution, in which case beta is 0, or it's not drawn from this distribution. Which is it? You don't actually know in this set of data. The only way of thinking about this is you only get one number. Suppose B is 6, right? Well, was it drawn from the distribution in which beta is 0? You don't know, right? There's no way of knowing. I mean, you didn't get an estimate of beta equals 0, but you wouldn't even expect an estimate of beta to be equal to 0, even if this were for sure the correct distribution of the results. Right. So what happens in this one setup? You don't really know, and that's important to understand. So the whole framework here is set up to try to enable us to have some uncertainty estimates in this weird sort of situation. Okay. Another way to think about this is what happens when n is large or totally under your control, like you can increase n or not. You know, you're running the experiment. You can decide whether to run more people through the experiment, or collect more data, or run on mechanical Turk for longer, or run the machine for longer, or whatever it is. What happens? What happens? Well, this distribution here, if you don't standardize it, becomes more and more peaked, right? And then it basically becomes easier and easier to distinguish anything from having come from this distribution. If you have 10 billion observations, it's very easy to know. You have to collect. It's very easy to know whether your data is coming from this distribution, because the distribution will be almost a spike, right? Until you divide by sigma squared, or by sigma. So when n is really large, your decision is going to be that the null hypothesis is rejected. Well, is that good or bad? Well, actually, it makes perfect sense, because if you have 10 million observations, you're very likely to be able to distinguish it from almost anything, including beta equals 0. And beta equals 0 is not a natural value of a parameter. It's just one value, right? It could be 0.00001. And if you have enough observations, you can distinguish it. But that actually, to me, throws the whole enterprise into question, right? So you've gone through this whole rigmarole, in this whole an enormous amount of effort, let's say, in order to collect your data. You collected lots of data, and you're able to distinguish it from 0. But the effect is so small that who could care, right? So I don't think, for most things in the social sciences, we particularly want to make the decision as to whether the thing that you're estimating is different from 0 or not. I think we want to know what the number is, and we want to know how uncertain we are about that number. Okay. A somewhat relaxed approach to Neyman-Pearson hypothesis testing sort of violates the rules a little bit in spirit, but people use it a lot, are p-values. So p-value is the probability under the null of getting a value as weird or weirder, as extreme or more extreme than the value we actually got. So if you look on here, it's the blue plus the red area is the p-value. So the test statistic is sort of observed, and this p-value is going to be, if the test statistic were here, the p-value would be 0.05. Here, the p-value is something like, I don't know, 0.15 or something, right? And so sometimes people report the p-values, and then what they do is they report your coefficients and your standard errors, and then they put these asterisks, which we call stargazing, right? Because they just put you put asterisks for 1 asterisk is for significant in 0.05, and sometimes 2 asterisks for significant in 0.01, and then they have 3 asterisks for even more significant. I mean, who cares really? Okay, what we really care about in most cases, not always, sometimes we actually do want to make a decision and it's just a decision and that's it. But very often in the social sciences, what we really care about is estimation. We want to estimate, come up with our best estimate of what the quantity of interest is, how uncertain we are about that estimate, any other values it could have taken with reasonably high probability or likelihood. I think that's what we would normally want. An important fact is that these three methods of hypothesis of theories, these three theories of inference actually are related. You can use likelihood to compute tests and p-values, and we'll do that. I'll show you how to do it. Okay, so what is the best theory of inference? You know, I've shown you three, and as you can now imagine, there's lots of others. What's the best theory of inference? Well, is it likelihood? Is it Bayes? Is it Neyman-Pearson hypothesis testing? Or should you choose what your list of criteria, like unbiasedness and consistency and efficiency, et cetera? Should you use finite or asymptotic-based theory? Should you use decision theory or non-parametrics-based theory or semi-parametrics or conditional inference or all kinds of other things that you don't have any experience with? Superpopulation-based inference, et cetera, et cetera, et cetera. Okay? And the answer is no, or none of these, okay? All right, anyway, that's a pre-programmed joke. The right theory of inference in a field in which we actually just want stuff that's useful. We're not doing normative philosophy. We want stuff that's useful. In a field where we're doing stuff that's useful, the right theory of inference is essentially utilitarianism, which is if it's useful, do it. If it's not useful, choose a different one. And it's okay to choose different theories of inference, right? Each theory of inference utterly violates the principles of the other theory of inference, right? Think about that. That's really wacky. So you have rigorous statisticians or social scientists using Bayes theory and other rigorous statisticians or social scientists using likelihood, and they completely violate each other's axioms and principles. But if one reviews the paper from the other, they usually think it's okay. You have to have one, you have to have something, you have to say what it is you're doing, but you can choose what it is, okay? So which one should we choose? Change the question to the theory of inference that makes it easier for you, right? Choose the one that makes it easier for you to get to your answer. Not the one that enables you to conclude the thing you want to conclude. That's just unfair, okay? But choose the one that makes it easier for you to run the computer program, that makes it easier for you to avoid this particular statistical problem. If choosing a prior is a useful thing for you, like in the example I gave you with our mortality forecasting example, that's great. Use Bayesian analysis. If choosing a prior is like an impossibility, don't do Bayesian analysis. It's okay. Do what's useful. That's the thing I would focus on. Methods for applied researchers are either useful or irrelevant. So that's basically what we should focus on. Okay, I want to make one point here. Theories of inference, even though they're fundamentally different from a normative perspective, they are sort of all moving in the same direction, not in terms of the principles, not in terms of the axioms, but in terms of what you get in the end, okay? So you can't bank on agreement on normative principles. In fact, I think there's never been agreement on a normative principle in society ever, right? Because there's always an incentive for someone else to come up with some reason to disagree so that you can attract people to your side. I'm at risk here of giving a political science lecture, but I think it's essentially political reasons why no one ever agrees on normative issues, or at least not unanimously. But even if there isn't, and I suppose even if there is agreement, it's not going to hold for long. There is an alternative convergence occurring that's worth you knowing about, and that is different methods giving the same result, and different theories of inference giving the same result, giving the same conclusion, and that's really important. Likelihood or Bayesian analysis with careful goodness of fit checks to make sure that you didn't just choose a model that causes us to come to a particular conclusion, and goodness of fit checks will do that. Or you can do various types of robust statistical inference or semi-parametric statistical inference, which you can think about in terms of the alternative model of representing systematic and stochastic components generalized. There were all those different parts. Well, some of those you don't actually have to specify ahead of time, like the functional form or the distribution. Some of those, sometimes, you can estimate the distribution, you can estimate the functional form. So those are different kinds of approaches. We're going to talk later in the course on matching for causal inference as a method of pre-processing your data before you get to parametric results. If you do that, that will often lead you to the same results. There's Bayesian model averaging. The idea here is if you don't know which model to choose, you can choose a whole set of models, and Bayesian model averaging is a particularly disciplined way of combining the models. There's committee methods and mixtures of expert models, which is a different way of doing a similar kind of thing. There's models with highly flexible functional forms, right, where you can't estimate the complete functional form, but within a very, very expansive class of functional forms, you can specify that rather than saying they're all linear or something like that. The key is that you can't trust any assumption. All theories of inference condition upon the assumptions, so data analysts always struggle trying to understand and get around them. Okay, so thanks for listening one more time. We're going to continue in the next lecture by getting into likelihood in much more detail. We're going to do examples and derivation and properties, and I'm going to show you how to forecast presidential elections within a likelihood framework. We'll talk about uncertainty in likelihood inference. We'll talk about how to simulate from likelihood models so that we can calculate any quantity that we're interested in and frame it any way we want, and portray it and present it to an audience in the most intuitive way possible. And we'll extend that framework then to a whole series of really interesting statistical methods. So thanks for listening again. We'll see you soon.